Let's begin by doing a quick recap of the previous lesson. We covered three terms that we're going to need to know for this unit. First one is voltage. Voltage is that force that pushes electrons through a circuit. I told you to think about it like pressure through a pipe. Next, we talked about current. Current is the flow of electrons through a circuit. And then finally, resistance, which is what restricts the flow. Then we talked about Ohm's Law. Ohm's Law is voltage equals current times resistance. And then we learned that you can use the triangle for this formula. All right, here's a quick review problem. It says find the output resistance of this laptop charger. And if you look really close here, the output resistance of the charger is not given, but we have a voltage and we have an amperage. Okay, so if we were to set this up, looking at our triangle, we're trying to find resistance. So resistance is voltage over current. And then let's go ahead and plug in our values. So the voltage is 19.5, the current is 3.9. So let's do a quick substitution here. And then if we get our calculator out, 19.5 divided by 3.9 gives us a resistance of 5 ohms. Now I want you to notice on the charger there are two values listed. There's two sets of values. There's an input and an output value listed. And what does that mean? So if you didn't know this, there are two types of current. You have alternating current, which is AC, and then you have direct current, which is DC. So many of the devices in your house will have both of these listed. And alternating current, AC, is what is used by the power company to transport the electricity to your house. We get really high voltages when we use alternating current, and it allows us to transport electricity over very large distances. So on the power lines, we're actually using AC, and that's what's brought into your house. Now, devices like your laptop can't handle a large voltage like that, so we use a device to take our alternating current and turn it into DC, which is what we use on our laptop chargers and around our house. So the next time you plug in your laptop, just know a lot of magic is happening inside that little black box, and know that the AC is being transformed into DC. So it's just one of those cool things that the more you know, right? All right, let's talk about circuit breakers next before we get into some math here. This is just something cool to note. So circuit breakers, since we're talking about current, circuit breakers are used in your house for your protection. You've probably seen an electrical panel in your basement, and the electrical panel has a bunch of little black boxes on little switches. And this happens to me all the time. I'm blow drying my hair, and at the same time I pull out the vacuum cleaner and start vacuuming. Both of those are plugged into the same electrical outlet, and the lights go off. All the power in the bathroom is dead, and you hear that little click. Well, that's the circuit breaker kicking in. So it used to be that you'd have circuits that would draw too much current, and it would cause things to overheat and catch on fire. So circuit breakers are designed to handle either 15 or 20 amps, and when they reach that limit, when they exceed that limit rather, it trips the breaker and it breaks the circuit. Okay, so that way we don't reach that danger point. All right, so we're going to run through a couple of examples today using Ohm's Law. The first says if the current remains the same, but the resistance is doubled, how does that affect the voltage? So what we're going to do is we're going to set this up with the voltage. So V equals I times R. And then it's telling us that we are doubling the resistance. So if we were to represent doubling the resistance, mathematically that would be 2 times R. So we just put a 2 in front of the R. Now, I've said this before, whatever we do to one side of the equation, we have to do to the other. So if we're doubling the resistance, we will end up doubling the voltage. And in the question, I want to just point out that it says the current remains the same. So we're not doing anything with our current. So we're just changing the resistance and seeing how that affects the voltage. Let's do another problem. If the voltage remains constant but the current is doubled, how does that affect the resistance? So this time we're looking at resistance. So using our triangle, resistance is voltage over current. And then it's telling us that we are doubling the current. Current, remember, is I. I don't know why they chose I. They like to make things difficult, right? So current is I, and we're doubling the current. So let's put a 2 in front of that I. Now, since the I is in the denominator on the right side, we need to put that 2 in the denominator on the left side. So it's going to be our resistance divided by 2. So notice that 2 is in both sides. And since we're dividing our resistance by 2, another way to think of that is we are halving our resistance. Oh man, somebody had a problem with animations on this one. Current is halved. You already know the answer. Let's go ahead and set this up. It says if resistance remains constant but the voltage is halved, how does that affect the current? So we're looking at the current here, which is I, and current is using the triangle, voltage divided by resistance. So current, I, is voltage divided by resistance. It's telling us the voltage is halved. This is definitely a tricky one because if we're having the voltage, that 2 is going to go in the denominator, so voltage divided by 2. Okay, kind of similar to the last one. Now, if the 2 is in the denominator on the right side, the 2 is going to be in the denominator on the left side. And there you go. So if you look, the I is being divided by 2. I, remember, is current. Current is then being halved. And that is all you need to know for today.